Okay, basically the stream should have been started. Tallinn University of Applied Sciences. Anyway, today we are going to talk about the basics of why are they necessary for the systems. Hello. Hi. So you are here for the first time here, yes? Anyway, we are going to know where the course is for that course, right? Or have you already registered yourself to the course?
Yes, I've signed in the course, but there are still some tasks.
Yeah. So anyway, the e-learning environment Moodle for this course, you have to search for the course in basically either in Estonian or you search for the course with those codes here. For example, MET280. So if you go to the home page, on the bottom of the home page, you find search for courses placed there. For example, MET280, go, and you should have two options here. The right option should be the lower one, and the password for you is capital F, capital I. Most of the text should be in English. For you at least. There are some text in Estonian too. Unfortunately, haven't had time this week to really clean up the course. But basically, the course has some practical work to do. So you are going to complete sets of practical exercises which give points to the final score. The point system goes from 0 to 100 points. So basically 0 to 50 is fail, and from there every other 10 points gives you another value in the score. So basically the practical part gives you about 40 points into the course. Completing theoretical tests here. These tests don't have limits to time or number of you receive 10 points for your score there. And finally, you have the final assessment here that will give you additional maximum 60 points. So you can theoretically 4 to 5, the good or excellent grades. It's not that hard to do that. So I lost a picture somewhere. Okay. So do you have any questions before we start? Do you have any previous experience with pneumatic systems? Nope. Okay, so basically,
I've done 5 to 2,
so basically you kind of have a head start at this topic.
yeah, maybe.
Kind of. But probably you will learn some theoretical background from this course, hopefully at least. Yeah. So this is a overview of a pneumatic system, of which we can kind of see that it's divided to two parts. The upper part here is kind of a production side where we produce pneumatic energy, and the lower part here is a consumer side of things. Generate in hydraulic and pneumatic system either pneumatic or hydraulic energy. We distribute it with a distribution system throughout the factory floor, for example, or inside the machine. The distribution system is for that. And in the end, we use actuators to we can compare it to electricity quite a lot, to both the hydraulic and pneumatic systems. For example, if you think about electricity, usually there is a power station somewhere. That's not the best drawing for the power station. Let's say we have a power station somewhere that generates electricity. We have some power lines going on the fields or below the ground somewhere, and the electricity ends up in our house where we can plug in some devices, for example electric motor, and there is a generator usually that generates electricity. And the generator is usually driven by something. So, for example, if we have a nuclear power plant and the turbine is driving the generator, so we use heat energy from the heat to generate we use the heat to drive the turbine, and the turbine generates mechanical energy. The mechanical energy is used to drive the generator, the compressor for the pneumatic system. The compressor uses mechanical energy to produce electricity to drive electric motor that generates mechanical energy, which in turn is used to drive the compressor. Same goes from the hydraulics. We have pumps in hydraulics. We use electric motors usually to drive to generate mechanical energy to drive the pump. So we're converting one energy to another. Of course, the hydro electric stations or whatever, basically. Or even we can use muscular energy by hand driving the compressor or a pump. The pneumatic energy with a compressor, and we are going to condition the energy to be suitable for the machines that are going to consume that energy. And in the end of the cycle or the end of the system, there's always an actuator or some form of device that consumes the pneumatic energy. It can even be just a blowing device, so we have a kind of a pistol-like device for blowing. We have a anyways, the idea is that in the end of the system we consume it, the energy. And usually in automation in factories we use pneumatic cylinders that generate linear movement from that energy. So linear movement, that means that and that's the basic kind of overview how we use that energy. We also have motors that generate rotational movement, but usually we use motors in hydraulics, a lot less in pneumatics. Well, let's dive into the production side first, and then let's talk about the consumer side. So we already know that there is a compressor that compresses air and produces that energy. But actually, in front of the compressor, there's actually another device, and which is not shown on the big, because compressor takes air from the atmosphere, and we kind of know that air in the atmosphere may not always be of the best quality. For example, sometimes when it's really dry and wind blows really hard, it can create clouds of dust in the air, for example. There can be insects in the air. There can be whatever leaves flying around in the autumn in the air. So we don't want to suck those things into the compressor. We want to filter these out first, so we don't destroy the compressor. So compressor takes the filtered air, and what the compressor actually does, the usual compressor, the most common compressor is a piston type compressor. So kind of almost the same setup as in car engines, internal combustion engines. There's a piston that moves up and down on the crank, and instead of, for example, in gasoline engines, we have 4 strokes of movement. Here we have basically two strokes. When the piston is moving down, it's opening a valve that brings air into the compressor chamber. The compressor actually compresses air. Actually compresses it. Even the screw type of compressors compress air, but there are some compressors that actually are not compressing what they are providing as kinetic energy. Anyways, these are just details. Air really suddenly, really fast. If we compress air really fast, really suddenly, with quite violently, what happens with air then?
The air heats up.
Yeah, of course. Air heats up. So the next element in
Press cold air and is getting hot. There is also some water, so some humidity from the cold air going in the compressor.
yeah. Completely correct. The humidity is a story by itself. The humidity is a problem, and we have to deal with it. But there is the percentage of humidity in air and the normal air pressure is one thing, and the other thing is when we compress air. The compressed air has another kind of percentage. Well, the ratios kind of shift. They're a little bit different than the humidity in open air. But yeah, when we compress air, cold air, dew point is really the percent. If we are close to dew point with the air that we are sucking into the compressor, then it's really easy to bring in some water. And usually the water starts to condensate out of the air that we're compressing is by cooling the air. if we cool the air, we are lowering the dew point, and if there is more water in the air that the dew point can handle, the water will condensate out from the air, so it will drop out of the air basically. But yeah, basically the first thing that element after the compressor, it can also be incorporated into the compressor, is the cooler. We need to cool the air down after compressing it. And usually with the cooling, also some condensation may happen, and some of the water must be of the system that kind of also has a function as a cooler, is a reservoir. But cooling the air is not the first and the most important part of the thing, this element, the reservoir. But the reservoir is for storing the energy. Some systems work so the compressor compresses air and fills up the reservoir. And if the reservoir is filled up, the compressor shuts down and waits for the reservoir to drain for some amount of time. And if the pressure drops in the reservoir, the compressor starts again to fill up the reservoir. So some systems work intermittently. That means that we are turning on and off, turning on the compressor and turning it off in cycles. So for some of the periods in those systems, mainly the point of the reservoir is storing the energy and smoothing out fluctuations in the consumption, and even actually even in the production. So if we use the piston type compressor, the compressor is not producing constantly. It's producing every cycle that's going up. So when the piston is moving down, it's not compressing air, not producing air. And if the compressor is or the piston, okay. So the main reason to use the reservoir is stays in the reservoir for a while. Some of the dust and some of the... So the next element in the system is a mains filter. And there may be more than one filter in the production side. There may be most of the dust and debris. Well, air kind of has to be clean. We'll talk about the quality of the air shortly. And one part of the quality is the filtration level of the air. And the last element in the production side is dryer. A dry is air, and basically it's taking out the water from the air. Usually...
Could you please repeat the third one? So which part is it?
Reservoir.
Okay.
That's the reservoir. The third part is the reservoir. And the main point of the reservoir is keeping a supply of energy stored in the reservoir. That means that we are filtering out the production if there are fluctuation in production, and we are filtering out fluctuation in the consumption. So basically, if we kind of think about the system as electrical system, then, well, what the hell? If you draw a comparison here, then a DC voltage using a rectifier, that means that we are getting some impulses of produced air, and by using a diode. So it's kind of acts like a rectifier in the electrical systems, like a diode. And to get a good quality DC voltage out rectifier. So the reservoirs are like capacitors in the electrical systems. They're smoothing out and filtering out the changes in pressure and flow rate. So the dryer takes the water out of the system, dries the air, and one option to do that is to cool the air down. For example, if we cool the air down to quite cold levels, we can draw out a lot of water from the air we have. There are other options to how can we try the air. We can use chemical kind of what do they do? They tie the water into the chemicals. They're basically like drinking it from the air. quite simplistic explanation, but you know those silica packages that you may get with some electronic devices, those packages that say that do not eat. In those packages there is the material that draws water from the air, so it's for keeping the package dry. The process is kind of the same here if we try to dry the air. So for the production side, the main goal for the production is to provide the system with the air with the required the air that meets the requirements of the system. So the air must meet some quality figures to, for example, 10 bars of pressure. The system pressure that goes into the distribution network. We have flow rate, so the system must provide enough flow rate for the if we use really large compressors. That's a wild card. I don't have a certain number for that at the moment. That's dependent of the compressor systems and everything else. Then we have the quality figures for cubic meter. One figure is oil, because compressors use oil. For example, if we use the piston compressor, it uses oil, and that oil gets into the system. So the amount of oil is a critical value in some cases, that we must get rid of some of the oil from the system. And the level of dryness, how much water is in the air. That's this pressure drop parameter. That means that how much does the pressure fluctuate throughout the use of this system. So for example, and So what's the lowest pressure and what's the maximum pressure of the system? And the pressure drop from the start of the system to the end of the system. That's also an indicator of the quality of the production system or the distribution system in total. So we need to think about those. Anyway, that's in general, that's how we produce the compressed air energy, pneumatic energy. Most of the compressed air systems use other systems that use compressed air in practice, not just factories.
I know about some cutting tools. They are driven by
Yeah, some hand tools use compressed air. And have you ever ridden a bus or a train? Quite a lot. And they also have main elements of the same system. They have compressor, they have the cooler, they have the reservoir, filter, kind of a canister looking element that's screwed into the system in some place and insured. So the most basic compressors you can buy from the hardware stores. You have the compressor, you have the cooler basically built into the compressor. So basically the piston is covered with fins to provide some cooling. You have the reservoir just beneath the compressor. Usually the compressor itself is on top of the... Usually don't have the dryer, but some of the drying process is handed to the reservoir. Some of the water will drop out in the reservoir, and you have a little valve on the bottom of the reservoir from where you can... Now for consumer part, well, the most important element of the system is always the actuator. So, well, that's basically the element why we are all we are producing the energy at all. If you don't have the actuator or the main consumer of the energy, what's the purpose of producing the energy if you don't controlled? So it can be, the movement of the cylinder can be changed in direction. So we need some kind of elements that change the direction of the movement of the cylinder. And these are directional valves. There are different types of directional valves and they have different purposes, but usually there are some 5-2 valves for controlling these cylinders. What does that mean? We will talk about that later. And to change the force of the movement, we use pressure valves. Pressure valves. So usually the the machine consists of the actuators, the flow control valves, directional valves, and pressure valves. There may be multiple actuators, there may be multiple valves, but the machine usually ends up in one point, the main air supply release valve. That means that if we shut the machine down using the pressure release valve or the shut-off valve, then the air that's in the machine will be let out. We usually have a thing called pressure regulator lubricant plug. That means that we have some pre-conditioning block that conditions the compressed air that's coming from the distribution system, conditions it so that it's suitable for our machine. So it has a filter. The filtration level of the air in the mains line may not be that clean, but we can make sure that the air going into our machine is as clean as we need. So we may have multiple filters here. Have filtered the air, we also want to set a certain pressure for the machine. So we have a pressure regulator in this block usually that sets the right pressure. That means the right force for our actuators. And of the, let's say, modern machines don't have that lubricator, but some do. And we can have all additional dryers in this. There are lots of options we can add here, but basically we have a block that preconditions the air that the overview of pneumatic systems and all the most common elements in the pneumatic systems. So we are distributing the produced compressed air energy throughout the system. What do you think? What happens with the efficiency, the percentage of efficiency? If we go through all of that, what do you think? What's the efficiency percentage in these pneumatic systems? If we put 100% of energy in here in the compressor through the filters, we lose some energy going through the dryer, and if we use the dryer actually consumes additional energy. So basically, if we put 100% of energy in here, we're basically we're adding some additional energy. For example, energy, if we calculate it like that, we're using additional energy in that part. The energy that's actually not doing anything special to the compressed air by actually consuming more energy. So it's a weird thing, but we're losing efficiency there. Then it's the distribution system that leaks, and for the leaks is the percentage of losses. If we have all the 100% of losses, then 20% out of those losses is leaks. And that's the best case scenario. Basically, the new system that's basically airtight. We have 20% of all the losses. We have leaks. Can we determine that there is a leak in the system? What's the indicator that we have a leak in the system? The constant hissing sound. So in some factories, when you visit the factory, basically that means that they're just losing money every minute, every second because of that leak that produces that heat. And we have some losses in the actuators themselves. And in the end, the basic point or the main point of the pneumatic systems is to get that linear action. And it's easy and cheap to get that linear action, and that's why it's still cases the pneumatic systems get changed out to fully electrical systems where they use electrical actuators. But usually the electrical actuators, linear actuators, cost quite a bit more than pneumatic systems. When they reach kind of the same level or the same point of money spent on the system, the graph is not the best graph here. It takes about 10 years before pneumatic systems start to get more expensive than the electrical systems. The compressed air system costs a lot more than using the electrical system and overall cost of the system. But we are making a assumption that nothing happens with the electrical system in that 10 years time. If the electrical some component in the electrical system, for example servo drive or the actuator itself, burns down and we have to change it, some thoughts about the compressed air system. Now let's compare that to hydraulic system. No, that's the same. Well, wait. Still the same picture. Hydraulic system. Basically, if the part that consumes hydraulic energy is really similar to pneumatics. The cylinder is basically the same, only stronger and tougher. The flow control valves are, in principle, they are the same. Construction wise they're different, but in principle they are the same. Directional valves, again, basically they are the same. Pressure valves, also in principle they're the same. So the control part is kind of the same. The actuators are kind of the same, similar at least. We have the cylinders and the motors here. Important difference in the systems is the production side. Because in hydraulics we use liquids, but in pneumatic systems we use that liquid in gaseous state. In hydraulics we use that liquid in liquid state. Usually we use hydraulic oils. That means that we have some kind of a reservoir, a tank that holds that oil we have in the hydraulic system. After being used in the system, comes back without any leaks. So hopefully we don't lose any oil throughout the process. Hopefully. So we have the tank here. Also we see a kind of a illustrated for usually either in actually mounted onto the tank or next to the tank or somewhere near the tank. Usually somewhere there is a pump. Give us kinetic energy. They give us flow rate, not the pressure. But now you should be asking that what are you talking about? Hydraulic systems have pressures too, and the pressures are quite high. The pneumatical system pressure is usually around 6 to 8 bars of pressure. In some cases 10, 12. To talk about how is that the pump gives only gives us only the flow rate? what's going on? Well, the flow rate is kinetic energy, and kinetic energy can be transferred to potential energy, and pressure is potential energy. So the pneumatic and hydraulic systems are constantly converting kinetic energy into potential and potential into kinetic. So it's just what comes first. Converting from potential to kinetic comes usually the first. So that's one of the differences, beside that we are using oils, liquids instead of gas in the system. The pump generates us the kinetic energy. The kinetic energy is converted into potential energy in the system by going plug the line. That's the most dramatic resistance. That's basically like driving straight through the wall, trying to go through a wall, basically. And that means that the kinetic energy that's transferred from the pump stops there and converts to potential energy, and we have the most pressure in this case. Now the problem is that if we have that kind of situation where we are meeting a wall, basically wall that doesn't move, that doesn't give the kinetic energy given from the pump just keeps converting into potential energy. That means that the pressure is rising. Hose here, or the piping, may explode. So that's not ideal, isn't it? So, but we don't see hydraulic systems blowing up every day, everywhere. We don't see construction equipment, excavators and bulldozers blowing up everywhere, every day. So we have some mechanisms to pressure relief valve that if the pressure rises to the set pressure on the relief valve, for example 120 bars, the valve opens and lets system from sudden rises in pressure, sudden stops, sudden movements, whatever may cause a pressure to rise, or the most common case is that the cylinder reaches its end position and doesn't move anymore. Therefore, the pressure rises to maximum, and we are releasing the overflow from the pump back into the tank. It's similar to a pressure regulator in pneumatic systems, but the principle is completely different. The relief valves set the pressure for all of the system. So basically, if we had two relief valves in the system, one set to 120 bars and one set to 100 bars, the 100 bars will be the set pressure for the system, because that will start to bypass the pressure or the flow coming from the pump before the one that's 120. So the lowest pressure, that means that it's keeping the system pressure high, while so the distribution system can be on higher levels of pressure, and the machine can be operating on lower levels of pressure. It's kind of regulating the output pressure. So we have the relief valve here. If we have the pump that's giving us enough flow rate, and we have the set relief valve here that's going to set the maximum pressure for our system, we have basically conditioned the oil for use in the system. That's the check valve. Flow control valves, check valves, go through the cylinders. And if they go through all that, the oil will finally return back through the return lines into the tank. But before entering the tank, usually the oil goes through a filter. Of course, the filter can be in different places in the system. Here it's in the return line. That's the cheapest. That's not ideal. It can generate cavitation in the pump. That's not good. We can use the filter in the high pressure, and the filter element itself must be able to take the pressure. And we can use return liners here, and we can use them in parallel systems connected to the tank. So there may be another pump on the tank which basically has the purpose of filtering the oil. So it's not using the driving oil through a filter, a separate pump and a filter there. It's also driving the oil through a cooler, additional cooler. So basically, if we have a hydraulic system that uses a pump that's, for example, the power of the pump, for example, is 20 kilowatts. 20 kilowatt pump. And the system is constantly in use. What happens with the oil?
The oil heats up too.
Yeah, of course. If we have high amounts of power, we have that means that we have of course in the system, hydraulic systems, we have also some loss valves, because if the liquid is traveling through the valve, there are small orifices that are restrictions. That means the friction of flow through those valves generate heat, as friction always kind of does. Friction going through the flow valves, friction going through the cylinder, all those frictions generate heat. And if we have a lot of power, that means that even if those percentages of the resistance kilowatt system, we basically should have 4 kilowatts of losses in the system. That means that that's generating a lot of heat. And where that heat ends up in, it ends up in the tank, of course, is kind of a radiator too. In smaller systems, the tank itself is enough of a radiator to keep the oil in acceptable temperature levels from the oil by itself. So we need separate coolers around the tank to cool the oil separately. So if the temperature reaches around 50 degrees Celsius, we should stop the machine. And if we are reaching 80 degrees, that's becoming a little bit dangerous. From the 80 degrees, the oil starts to lose its points in the system that may be quite hot, actually, hotter than 80 degrees. Well, we are talking about the temperature in the tank, that means some points in the system are even more hot than 80 degrees. Change its structure, internal structure, which may mean that it starts to lose its lubricational capabilities and corrosion resistance capabilities and so on. It starts to lose its structure. So we don't want to automotive oils that are used in the car engines usually operate at 80 or 90 degrees Celsius, but these oils are designed to work in these conditions. So that's something to keep in mind. Okay, what else? Yeah, of course. Differences between hydraulic and pneumatic systems. Usually, the ideology behind hydraulic systems is that we're trying to keep the production as close to the actuator as possible. The closer the pump to the cylinder, the better the efficiency. The efficiency itself is, let's say, starting from 70% going up to 80%, somewhere there. It may be lower, maybe higher. The general kind of region is somewhere there. Much better than pneumatics, of course, but the problem with hydraulics is that trying to push liquid through a pipe of liquid, the flow itself has restriction. Well, basically it's viscosity. The more viscous the liquid, the harder it is to make it flow. So, and of course, if we talk about viscosity, if you compare viscosity of a gas to a water, basically, the level of viscosity is dramatically different. Gas is basically tens of times less viscous than liquids. So the loss we get from the moving the oil through the system is was it next month or starting in November or something like that? We will have the lab lessons, and in the lab I can show you an example of using a short about 1 bar of pressure loss for 1 meter of hose in our system. So if we have a 2-meter hose, it will have 2 bars of pressure drop over that hose. The pressure drop means that we are losing energy just by moving the liquid through that hose. Not ideal. Anyways,